Hi, it's Kevin again. I'm back to continue our exploration of building a software Hollerith card reader using a document scanner and image processing. In this episode, we'll be working on preparing the image for analyzing geometry, so the next time we can recover the location and orientation of the card. In the last video, there should be a link nearby. We used a statistical technique called k-means clustering to come up with a Boolean value for each pixel, indicating whether the pixel was on the card or on the green screen. The binary image that resulted looks reasonable visually. Now let's do some basic image preparation tasks to bring it to a form where we can analyze the geometry. The first thing that we should notice is that the binary image still isn't entirely clean. Let me magnify the top right corner and show you. There's a fair amount of speckle in both the card and the green screen. The edges of the card and the holes are quite ragged, and some of the print on the card is bleeding through the classifier. It turns out that none of this is a huge problem. It's quite easy to remove this sort of noise. We'll use what's called a median filter to get rid of it. The idea behind median filtering is to look at each pixel together with the neighborhood surrounding it and take the median value of the pixel and its neighbors. If the data are binary, this rule is equivalent to giving the pixel and its neighbors each one vote and using the majority. In the examples, I'll show a neighborhood that's a 3x3 square, but the neighborhood can be any size and shape as long as it's symmetrical. Let's see what happens in some common cases. Obviously, solid areas of the image are unaffected. The edge of a solid area is also unaffected if it's orthogonal, or even if it's diagonal. Even an oblique line or the edge of a curved area will generally stay the same. But isolated pixels, or clumps up to 2x2, get deleted. Projecting corners, whether vertical or diagonal, get shaved off. And filament-like features, at most 1 pixel wide, get removed as well. This technique also works to denoise quantitative data, and since the median is an order statistic, can be used on ordinal data as well. If you have categorical data, that is, that sort the pixels into types with no particular order defined among the types, I'm afraid you'll have to think of something else. Maybe a future episode will confront data like that. Let's take a look at what happens when we apply the median filter to the roughly segmented image. The pixels shaded in orange are the ones that lose the vote and get turned off. They include nearly all the white speckles and the pixels lying outboard of the ragged edges. The pixels shaded in blue also lose the vote and get turned on. They include the hairline feature, the black speckles, and the pixels lying inboard of the ragged edges. The result is a much cleaner image, with the contours of the main features being hardly affected at all. The next step is to label pixels in the image according to whether they're on the edge of the paper. The precise position of an edge is always a little bit uncertain, because generally edges of physical objects will never align precisely with pixels in a picture, and because there's also always some amount of uncompensated optical distortion in any picture. It turns out that we'll shortly be dealing with a geometric algorithm that's also somewhat imprecise. We will deal with all of this by having an imprecise measure of what is an edge. We'll start by blurring the image. Next, we'll differentiate the image along the x and y axes. If you don't know what differentiation is, just know that we can do a brutal version of x-axis differentiation by setting the new value of a pixel to half the difference of its left and right neighbors. And similarly for the y-axis. If we compute the squares of the x and y differences, add them up, and take the square root, we get a measure of how edgy a pixel appears to be. The result is an image of the entire card, labeled with our edginess score. All of what I've shown here is fairly routine work that gets done on all sorts of segmented images. If I do further videos on image segmentation, I'm likely to refer back here because all of these operations are so fundamental. And with that, I'll end this episode a little early, because the next step is considerably more complex than any of the half-dozen operations I've discussed this time. Thanks for following along with me on this journey toward decoding punch cards. Next time, we'll be looking at an algorithm to find straight lines in an image of the edges, and how to use that algorithm to establish the coordinate system of the card. So stay tuned for that. Until then, stay safe, stay healthy, and keep calculating.